Hi everyone, welcome back to Operations Research. So in this last video about the simplex method, we're going to discuss an implementation issue of the simplex method. So far, basically we use the Tableau approach for calculating everything we need in running the simplex. And now we're going to describe another way which is actually implemented in most computer softwares. It's the metric way of doing the simplex method. So as we mentioned, this is an implementation issue. So the algorithm itself is not changed in this implementation or in that implementation. It's something similar to you have an algorithm and you choose different data structures or different languages to different data structures to implement a particular algorithm. Okay, here is something similar. You do not change the concept, but you change the way you do the calculations. So let's start. When we implement the simplex method with computers, then typically using Tableau is not the most efficient way. What's more efficient is to using matrices directly, and that's the topic in this video. We're going to tell you how to do that, and in a very short description, how it is more efficient. So the standard form linear program is something we want to solve, and it can be expressed in this way. Okay, originally it is a usual form: minimize C transpose X subject to AX equals BX non-negative, and we may split variables into XB and XN and split the C vector and the A matrix accordingly, and then do some algebra, we can get this. I hope you still have that image. And then if we change or organize all those numbers into a Tableau format or the linear systems, then we have this. Okay, this is still something old, and you have seen this in the past. For basic variables, at the constraint side, there is an identity matrix, and at the objective side is 0. For non-basic variables, the coefficients, this thing, are called the reduced cost. And finally, XB, the basic variable's value, can be calculated as AB inverse B. In any situation, this number CB transpose AB inverse B is the value of the current objective function. Okay, so we may do matrix operations to do iterations instead of doing Tableau algebra. What does that mean? Given any basis B, you will be able to find, for example, AB and AN, and then you do AB inverse times AN, you will be able to calculate all the coefficients for XN. For the reduced cost, is the same thing. Given B, you may find CB, CN, AB, AN, and then you do this and directly get the coefficients for XN. Okay? And that's the main idea about using matrices. Because we have this formula, so we may, given any basis, do some matrix algebra to get everything we need in this system. And then we may make decisions accordingly. For example, from here, we know who should enter. From here and here, we know who should leave. Let's see something in details. So, given any feasible basis, we know the current basic feasible solution is determined in this way. XB is just AB inverse B, XN is 0, and the current Z value is CB transpose AB inverse B. Okay, something we mentioned. According to the Tableau, you know this. For the entering variable, so the way to determine an entering variable is to see the reduced costs. Okay, these reduced costs are exactly these things: CB transpose AB inverse AN minus CN transpose. So given B, you calculate this vector. Okay, we somehow call it C bar N, and you calculate this vector to see whether there is any reduced cost that is positive. Okay, that is positive. For this minimization problem, A positive reduced cost means you may enter that variable to get some improvement. Okay, so we first calculate this vector, and in that vector we search for any element that is positive, and then we know which variable should enter. For living variables, if we say xj enters, then the ratio test is to take the right hand side vector, okay, the right hand side vector, and one basic column, okay. The basic column is the column that is under the entering variable, okay, under the entering variable. Here, AB inverse is a square matrix, AN is another matrix. But if you take only one column from AN, okay, you take only AJ, then AB inverse AJ would be your entering column. And then you do this ratio test, okay, ratio test, to get all the ratios you need. The basic variable that should enter, should leave. The basic variable that should leave satisfies the following situation. First, the denominator must be positive, okay? And among all those rows whose denominator is positive, the ratio should be lower than them, okay? The ratio should be lower than them. That's exactly the ratio test. The key is that AB inverse B is the right hand side, and AB inverse AJ for some non-basic J is the entering column. So that's why given any basis, we know how to do entering and leaving variables. Once we know that, we get to another basis, we can get, again, those new reduced costs and the new ratios, and then so on and so on. So when do we stop? At any optimal basis, we know that it must be the case that the reduced costs are all non-positive. Otherwise, we will enter something else. Okay? At the optimal basis, this particular thing must be non-positive. And then the optimal basis can be found as the current AB inverse B and 0. The current objective value can also be calculated. If there are multiple optimal solutions, what we're going to see is that first, the current solution is optimal. Okay? Just like this one, the current solution is optimal. And there exists J such that C bar J is 0. There exists one non-basic variable whose reduced cost is 0. Okay? And that tells us there may be multiple optimal solutions. To detect unboundedness, we know there should be a non-basic variable having a positive reduced cost. So we have an improving direction. And then all those numbers in the entering column or all those denominators are less than or equal to 0, so that this improving direction is unbounded. Okay? So using matrices, we can detect everything we need. So let's do this example again with matrices. We have these 3 constraints, 5 variables in our standard form. Originally, these 3 are certainly less than or equal to constraints, with here one identity matrix adding into the original program. We now have a standard form. In the matrix representation, what is exactly what we're going to do? We first write down C, A, and B. A is nothing but all the coefficients adding into a matrix. Okay, so you can see that A for the first column is 2, 2, 0, 2, 2, 0. The second one is negative 1, 1, 1, negative 1, 1, 1. Okay, for C, C itself is a column vector. So we do a C transpose to make things clearer. C transpose is nothing but all the objective coefficients, so only 1, negative 1. B is the column vector for right hand side. Okay, so given any LP in standard form, we may do this. And then given any basis, we know how to split C and A. Suppose, for no reason, I tell you that I want to try this particular basis xb, which is x1, x4, and x5. Then xn is certainly x2 and x3. Then we do a split like this. For AB, I collect the first, the fourth, and the fifth columns in the matrix A, which are exactly these three. For AN, I take the second and the third columns in A. For CB and CN is similar, okay? And then I can get these 5 components according to the original formulation, according to the original program. So, given this basis, we then calculate the following things. The current basic feasible solution can be calculated as AB inverse B according to this formula. Okay, we have AB here, so AB inverse can be found by hands or by pens and pencils. Okay, so you have this, you have AB inverse, and then AB inverse B gives you the values of basic variables x1, x4, and x5 should be 2, 4, and 3. You may want to verify that when you use Tableau, when you get it, when you use this basis, you have exactly the same thing. For the z value, again, CB transpose AB inverse B can be used to calculate the z value. CB transpose is this one. Okay, AB inverse B has been calculated by you, and this is 2, 4, and 3. So your current objective value is -2. Current solution 2, 0, 0, 4, 3 can be verified by yourself. For non-basic variables, we want to calculate their reduced costs like this, okay, according to this basic formula. So CB, you have it. AB inverse, you have it. AN are just the 2 columns, the second and the third columns from the matrix A, you have it. CN transpose, you have it. Combining everything here, you get 1/2 and a -1/2. That directly tells you that x2, this variable should enter, because it has a positive reduced cost. And then we need to do a ratio test. So first we need to find the numerators, okay, the right hand, there are 2 things to get. The right hand side column and the entering column. Let's see the right hand side column first, okay. We know AB inverse B should be put at the right hand side, and 2, 4, 3 is the current values of the basic variables. And then we need entering column. Entering column is here, okay. AB inverse A2. Here we know it should be A2 instead of A3 is because x2 is entering. A2 is the column, is the second column in A, which can be found also here, right? This is X for x2, this is for x3, and we need A2 here. AB inverse A2 can be calculated as this. This must be the denominator we need. And here, AB inverse B, okay, is the right hand side column. We do ratio test to get 2 divided by -1/2. This cannot be done because the denominator cannot be 0. Cannot be non-positive. So for the second and the third row, the first ratio is 2, the second ratio is 3. So this particular row, okay, x4, the second row corresponds to x4. x4 should be the living variable. Up to here, probably you get the first idea about why using matrix may be more efficient than doing Tableau. When you do Tableau, you need to calculate any number in the Tableau for every iteration, right? But for using matrices, here, for the denominator, you only need that entering column. You calculate these 3 numbers because you know x2 should enter. And that exactly means you don't care about AB inverse A3. You don't need to calculate that 3 numbers below x3. Okay? But in Tableau, you need to first calculate any number. While in using matrices, you only calculate those denominators when you have an entering variable. Okay, so if the matrix is pretty big, then this certainly can save you some time. Okay, but that's not the key point, but here is something that you may understand. Okay, so now given another basis, we may repeat everything. Here, when the basis is x1, x2, and x5, we take the first column, the second column, and the last column into AB. And then we take the third column and the fourth column into AN, and other things the same. Given this basis, again, XB and Z can be calculated accordingly. AB, we have AB inverse, and then multiplied by B, we get x1, x2, and x5 should be 3, 2, and 1. Similarly, Z can be calculated. So the current basic feasible solution would be this one, 32001. Now, for xn to be x3 and x4, we may again calculate the reduced cost. I have CB, I have AB inverse AN, and minus this guy. Just a reminder, even though the formula looks extremely simple, you need to do calculations accordingly. Okay, when you have an inverse request, you need to really calculate that inverse. Also, this formula looks the same as what we did 2 pages from now. Okay, but numbers are certainly different because the B and N are different. When you have different B, you take different columns in A to get into the matrix AB. You take different components in C to get to the vector CB. And for CN, AN is the same thing. So the formula is the same, but as long as B and N are different, as long as the bases are different, then your result would be different. Here, no variable should enter and the basic feasible solution is optimal. We can make this conclusion even without calculating anything in the denominator side, right? So again, save some time. In short, the simplex method may be wrong with matrix calculations. In this way, the bottleneck is the calculation of AB inverse. We all know that if the matrix is very big or the size is very large, then calculating AB inverse can really take a lot of time. Okay, and if we use a very naive implementation, that means given AB, you calculate AB inverse. Given another AB, you calculate another AB inverse. If you do that in every iteration, then using the matrix way may not be faster than using Tableau because calculating AB inverse is really too time consuming. However, there are some observations we may have. That in any iteration, if I have a current basis and then I look back to the previous one, we know only one variable would be different, and that means the current AB and the previous AB has only one column different. Okay, so at here, I certainly know what's the previous AB inverse, and given that I want to calculate the current AB inverse, that would be much easier than doing AB inverse according to my current B from scratch. Let me say that again. One naive way is that I give you AB, you calculate AB inverse directly without any other information. Okay, that takes a lot of time. But if you remember that you have the previous AB with only one column different, and you have the previous AB inverse, you take those information into consideration when you calculate AB inverse, that can save you a lot of time. Okay, that's the key idea here. So when you implement the simplex method with matrices, you do so to save time in calculating AB inverse, and that can eventually make the matrix implementation dominate the Tableau implementation. Okay, that's the key idea. Actually, up to here, probably you want to ask one question. The previous B makes you AB matrix, and that AB matrix is certainly invertible. But after we change one column, how may we guarantee that the new AB matrix is still invertible? Okay, that seems to give you some questions, right? We know among all those bases, some are infeasible because the corresponding AB matrix is not invertible. How may we guarantee that we take one column and change it to another column? How may we make sure that always we can get an invertible AB? Okay, that's something in some sense you need to answer, right? So, as this is just an introductory course, I'm not going to tell you how to calculate AB inverse faster. I'm not going to tell you or to prove to you that AB will always be invertible. These are certainly interesting questions, and I encourage you to think about them. And if you want to get some answers from me, yeah, that's also certainly fine. Maybe you may find me in my office hour or anytime. Okay, so with this, we have completed our discussion about the simplex method. You know how to formulate any problem into standard form. You know basic solutions, basic feasible solutions, you know basis. And then you know the basic idea of the simplex method. Geometrically, you run among extreme points. Algebraically, you find entering variable, you find leaving variable, you do iterations, and finally get to the optimal basic feasible solutions. Okay? In this lecture, we discussed something more advanced. You know how to detect unboundedness and multiple optimal solutions. You know how to do two-phase method or two-phase implementation to find an initial basic feasible solution or show that there is no feasible solution. You know what's the impact of degeneracy. There may be no improvement, there may be no cycling. And then you know the smallest index rule is useful for removing cycling. And you know some efficiency issue about the simplex method. In particular, number of constraints is more critical than the number of variables. And finally, you know, if we want to do the simplex method in the most efficient way, we need to use matrix algebra instead of Tableau. Tableau is easier to understand if we are not familiar with matrices, okay? But with matrix, everything is more precise and the implementation can be faster if we use a better way to calculate AB inverse and so on and so on. Okay, so that's the end of this lecture. Thank you.